All right, hopefully this will help some of you out, especially if you've been absent or you can't quite remember what happened in class. But we're going to be thinking about this particular fourth degree polynomial. Now again, we know that it's fourth degree because the largest exponent we see is a 4. And that's significant because it tells us a little bit about the end behavior. Recall that whenever you have an even degree function, then the left and right end behavior will be the same. The left and right end behavior is the same. Again, that was because we have an even degree. So once we know that they're the same, the next step is to figure out what actually the end behavior is going to be. And for that, hopefully you recall, we focus on our leading coefficient. All right? 2 is greater than 0, which of course means it's positive. If you have a positive leading coefficient, you know that the right side of the graph goes up. So therefore, the right side rises. Now, when we describe that symbolically, you want to recall that we actually mentioned the fact that it's rising before we mention that we're talking about the right side, because it's the polynomial's behavior or the function's behavior that we're interested in discussing. So for that, we're going to say that the function values approach positive infinity. The graph is rising. And then as x is approaching positive infinity. Recall that x approaching positive infinity is how we indicate moving towards the right. Because the end behavior is the same, we can now easily describe the left end behavior. The same means the left side is also rising, but now x will be moving to the left, which means that the x values are getting smaller and approaching negative infinity. All right. So remember, end behavior is dictated by both the leading coefficient and the degree. Right. Then the degree also plays a role in the number of turns that the graph can possibly make. If you recall from the packet that we worked on when we first began discussing end behavior, you know that a quartic function can actually look a lot like a parabola. So it's quite possible that a quartic function will only have one turn in it. So again, it's not technically a parabola, but it looks much like a parabola. But it's also possible for a quartic function to have more of a W shape, where we have 1, 2, 3 turns in it. And of course, it doesn't necessarily have to be symmetric. It's possible that the shape is a little bit more asymmetric, where we have 1, 2, 3 turns again. So you want to bear that in mind as you start to investigate the behavior of the particular polynomial. All right, well, what else do we know about this particular polynomial? Well, one thing we know about all functions is that if we plug 0 in for x, we'll find the y-intercept. Right? In this particular case, f of 0 is equal to negative 30, so we know our y-intercept is 0, negative 30. All right. And as far as x-intercepts are concerned, well, if it's fourth degree, then we know there are 4 zeros. Remember, the fundamental theorem of algebra leads us in that direction. So this thing has 4 zeros. And then you want to consider, well, what are some of the possibilities for those zeros? Numbers like 7 and 8 and 9 aren't possible. But if you remember the rational zero theorem, you can make a list of everything that is possible. Recall that we're going to take factors of the constant. So factors of negative 30 give us plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, 10, 15, and 30 as all of the possible integer rational zeros. But remember, rational means fraction, so we also have to consider the factors of our leading coefficient. Now in this case, that's only 1 and 2, but that does add the additional fractions of 1/2, 3/2, 5/2, and 15/2. So any of those are potential candidates. Again, years ago, students simply had to start guessing and checking and guessing and checking. Since we have technology, we're actually going to go ahead and get a look at the graph to basically get a hint as to where we should start to guess. So here we have our picture. Now in this case, we have a nice window that goes from -32 all the way to +32. Right. And that allows us to see that in this particular instance, there are only two visible zeros. All right. This is, again, somewhat parabolic looking. There's no way this thing is a W where it turns around and crosses the x-axis somewhere else. If we can zoom in a little bit, we'll get a better look at where those particular zeros are. All right. So that should reveal to us that we have a 0 at -2. Or if you prefer, we have an x-intercept of -2, 0. And another over here in between 1 and 2. Now if you think for a minute, 1.5, obviously in between 1 and 2, and as a fraction, that would be 3/2. That was one of the values in our list of possible rational zeros. So very quickly, we notice that we have these two x-intercepts, or two real zeros. And the key there is that they're real. This was a 4th degree function. If it's 4th degree, it has to have 4 zeros. But there are only 2 visible zeros. Well, that means that the other 2 zeros must be imaginary. All right. Now recall, we first started discussing imaginary zeros when we were looking at the square root of a negative number. Now, the square root implies a quadratic equation. And the only way for us to discover what the imaginary zeros are is to rewrite this as a quadratic equation. All right. So what we got to do is start doing some synthetic division. So our first step then is going to be to divide our initial polynomial by the first 0 we saw, which was -2. So remember that you want to translate the polynomial into coefficients. So 2, 5, 6, -7, and -3. The 2 comes down. We multiply for -4. We add. We multiply. Add. Multiply. Add. Multiply. And add. The 0 reassures us that we're doing this properly. Well, at this point, we've reduced our quartic equation to a factor of a linear term, or a factor, I guess, of a linear term and a cubic term. Might be the best way to put that. Well, we're going to continue now and divide by 3/2. We do this with the quotient that we just received. So the 2 will come down. Right. Multiplying 3/2 and 2 gives us 3. Adding those gives us 4. Now 3/2 times 4 is 6. Adding is 10. Multiplying is 15. And once again, we're reassured we're on the right track when we get 0 for the remainder. Now the key to this problem is interpreting what we've just done. And so we're going to take our initial polynomial and we're going to try to factor that using this as our guide. Let me make the shape a little different here so I have a little more room on this slide. All right, so what we'll do, initially we had f of x was 2x to the fourth plus 5x cubed plus 6x squared minus 7x minus 30. Now, since we were dividing by -2 in terms of the synthetic approach, that means we have a factor of x plus 2. And the result of that division was over here. We're going to translate those numbers into a polynomial. We have 2x cubed plus x squared plus 4x minus 15. Now that 2x cubed plus x squared plus 4x minus 15, if you were to try to factor that by hand, it would be kind of tricky. Grouping isn't really going to work. But we have the key over here. We were able to divide it. We were dividing it by 3/2. Now, as a factor, that would be x minus 3/2. And our quotient, 2x squared plus 4x plus 10. Now hopefully when you see that quadratic, you do see a common factor of 2. And we use that common factor of 2 to rewrite our middle term with the fraction. We're going to pull the 2 all the way out and use that 2 to multiply the individual items in this one term. We wind up with 2x minus 3, x squared plus 2x plus 10. Now, a quick check. If you were to look at the first item in each of these factors and multiply those together, you would indeed get 2x to the fourth. Likewise, if you were to multiply the last term in each of these factors, you would wind up with our constant term of -30. So there are lots of reminders along the way that you're doing a problem correctly here. All right. So if our directions had been to factor this polynomial, we would be done at this point. We have it factored. We know that x squared plus 2x, well, there's a mistake there, isn't it? X squared plus 2x, I didn't even catch it with the multiplication. Sorry about that. X squared plus 2x, whoops, plus 5. Makes a little more sense. I apologize for that. But we know that can't be factored. But we also know any quadratic equation can be solved. Right? In this case, we're going to finish this up by solving that quadratic using a technique known as completing the square. Because we know that the quadratic formula is for mental lightweights. And nobody wants to be a mental lightweight. So we'll start by moving the constant to the right-hand side. We'll take half of the linear coefficient, so half of 2, and square that to determine the missing piece. So in this case, 1. Anything we add to the left-hand side, we also add to the right-hand side. We factor the left-hand side and simply simplify the right. When you take the square root of both sides, do not forget to include the plus or minus in front of the radical. Right. And then recall that the square root of -4 is 2i. So we have -1 plus or minus 2i as the solutions to this quadratic equation, which means ultimately that the zeros of f are -2, 3/2, -1 plus 2i, and -1 minus 2i. And that's it. All of the problems of this variety will require that you identify the potential zeros, investigate to find the actual real zeros, and then do some division to determine the value of any of the imaginary zeros. Thank you very much. Hope you understand.